here we have our sonar point cloud building system featuring the KL25Z microcontroller, which acts as a ADC sampling from an ultrasonic range finding module, which is then fed over a serial connection after doing peak detection using the Z-score filter to the BeagleBone Black wireless, where all the heavy computational power happens. We are on the BeagleBone wireless, sampling from a MARG sensor, which is, I can't remember what the acronym is anymore, but we're 3-axis accelerometer, magnetometer, and gyroscope. That data is being fed into the Magic sensor fusion filter, which combines all that data together into a quaternion, which I don't know what a quaternion is. It's some crazy math stuff. We convert that into pitch and yaw, which would be up and down, side to side, and then create a XYZ unit vector and map it into a bitmap pixel data, which is then exported as a series of TIFF images, which we transfer to the laptop computer and view using Fiji, a scientific image processing and viewing program where we can view it as volumetric data. So what we're going to do here is we're going to capture some data from this wonderful setup of chairs, and then we're going to look at the data on the computer. So let's kick it off. This is going to be the most boring part of the video. All right, we're going up and down, or really I'm saying the opposite of what I'm doing. And left to right, we're painting it with sound. Now the sonar module is by definition noisy, as in it sends out noise and measures noise back. Unfortunately, it measures lots more noise than we want to get back. So what we're doing with the Z-score filter is trying to find the peaks in the data. Doing a raw capture of the response from the sonar module. There's too much data to transfer over the UART at a reasonable speed. So to get a decent sampling rate, which is still at a measly 5 hertz, we are doing peak detection using, as I said, the Z-score filter. So the Z-score filter keeps a running average. We're using a 5 sample window, as well as the standard deviation of that window. And as we receive a measurement that is outside some thresholded multiple of a standard deviation from the mean, that moving window mean, then we log it as a reflection, or as a peak. So what happens is sometimes we get close to stuff, we're supposed to be staying momentary because we're not tracking motion. So this is from a stationary standpoint. We do get a lot of reflected noise with the sonar module. Also moving it, especially back and forth, you kind of get that Doppler effect and really weird data back. So this is something that could be filtered out better with some parameter tuning in our Z-score filter, but we didn't really get there. So doing the best we can. We're still painting. We're painting chairs. As we only get a few points back from each bounce, like at the most typically 5 to 10, and really there shouldn't be 5 to 10 objects here. We just have a few chairs, but there's all this other stuff in the room too. So, and sound doesn't go in a straight line like a laser. It goes as wherever, the cone of uncertainty. So we get a lot of stuff back. So we're still painting. The more we get, the more pixels we show up. As in, some of it's good, some of it's bad, but that's probably pretty good.
All right.
All right, so we're going to stop the program. And then now, our program, once it's done collecting, converts that data into a series of TIFF images, as I said. So we're now going to transfer that data over, whoop, not that window. I'm going to hide my secret stuff. We're copying it over our USB connection. Wow, so fast. 3 megabytes per second. And then I'm going to close this other from a previous run of data. And now we're going to open up in Fiji. Fiji is just ImageJ. It's the worst acronym for a program ever. So we're going to import this as a series of TIFF images as a stack. And as we see, we've got this beautiful field of black. Let's blow it up here. So there's some points, there's some points. As we get closer to the center of the image, the points start to cluster. We can pretend that these are actually accurate representation of these chairs. And get closer and closer. And as we see, we're about right in the middle of the image now, which makes sense. So our frame of reference in this bitmap, so it's a three-dimensional bitmap, cube. So most of the noise you get is going to be close to this, well, I mean, most of the data is centered. So we're really from the middle of the image, bouncing out and reflected out. We use a sample, we collect 2,000 samples for each ultrasonic burst, which translates to about 4 meters, which is the effective range of this ultrasonic module. So here we got some more pixels. So let's switch over to the volumetric view using this handy dandy volume viewer plugin with Fiji. Fiji's a really cool program, by the way. Lots of biologists just love it. So let's see if we can change this to a colorful lookup table, and we can see as a view our data. So here's some sliced images on the side as we can see it from different angles. Before we were just going in the Z dimension, which is that, and Y, and again, as you can see, it kind of gets focused around from the center. There's kind of a dead zone in the middle. That's because we're ignoring some of the first cluster of samples, which as you start with zero initialized data, the filter picks up stuff as it's getting warmed up. It's interesting we get this strange little slice as we get to the middle in the XY plane. But as you can see, we're not really getting, you know, it isn't a painting of these chairs by any means, but, you know, it's something. So what we could do to improve this system is spend a little more time tuning the filters that we have. Both the Magic filter and the Z-score filter are parameterized and are intended to be tuned as you get an idea of what sort of data you're getting back. Additionally, the signal to noise ratio that's output by the ultrasonic transducer on the receiving side is pretty low. So we're getting very low voltage readings. Even so, we did end up using a voltage divider to scale that down because it theoretically could be up to 5 volts read into a 3.3 volt microcontroller. Even just reading straight out of the output, it's about the same. So you have a really low noise floor. Otherwise, you know, there's certainly room for improvement, perhaps using a laser as opposed to sound. That would give you actual straight line points. Granted, that would not give you the opportunity to see past that point. It'd be interesting to see if we did the same thing, and instead of reading the analog output of the transducer, instead we use the digital signal, which this range module intends us to use, which basically, on its first impulse back, it triggers a digital signal to transitions from high to low. So you read that falling edge and say, okay, that's where my object is, and that's really kind of what this thing is intended for. Also, it's intended for larger objects, so testing with like your hand and cell phone or even like a textbook kind of isn't a large enough object to get a good idea of the object that you're reflecting against. But there we have it, coming from Francis and David, and we are thrilled to have had this experience of designing this relatively complex ragtag crew of processing powers and sensors together. Thank you very much.